All right, in this video, we hope to finish the chapter on boundary conditions using Lax-Friedrichs. So last time I talked about how to impose transmitting boundary conditions using Lax-Friedrichs. This time I'm going to show you how to do that using absorbing boundary conditions. So in absorbing boundary conditions, as we talked about, the concentration has to be zero, or whatever the variable is has to be zero. That is called absorbing boundary, as we have on the notes. So for implementation, what we do is in Lax-Friedrichs we have the generic equation right here from point 2 to n-1. We do not include point 1 and point n because those are boundary points, and we need to deal with them using absorbing boundary. So for the point at x equal 1, or well, x equal x1, or the left boundary, that has to be 0 because of absorbing boundary condition. And we do the same thing at the last point at x equal xn. We're going to use the concentration equal to 0 at any time tn plus 1. By setting the concentration equal to 0 at these 2 points, we apply the absorbing boundaries. So let's run the code for an alpha which is less than 1 to be in a conditional the conditional regime because of the CFL condition, if you remember. Alright, so alpha is positive, so there's a traveling wave from left to right. It's going to hit the boundary and it should be completely absorbed. So watch this point. The concentration here has to be 0, and you see that it's always 0. But because of that, the artifact of that is this little weird peak that actually shows up. Although it doesn't stay for long, but at the time that the wave hits the boundary and goes through it and completely gets absorbed, this peak actually shows up, which is completely, a numerical error. Again, it's not big, but that's what it is. So let me rerun the code. So there you go, there's a traveling wave, it hits the wall, and you see that we manually actually put the concentration equal to 0 here to be completely absorbed. We can flip the direction of the wave, and if I put a negative sign here, then you see that now my wave is going to go from right to left. It hits the wall. The velocity, or the concentration is equal to 0 here, and because of this boundary condition, the way we implement it leads to that small error as wave actually hits the boundary and goes through it. The error does not propagate into the domain, but actually shows up only at the point that we impose the boundary. Okay, so I think with this, we can now close the chapter for boundary conditions, and for next time we can talk about how to use finite differencing to solve wave equation and diffusion equation. So wave equation can be written as the second derivative of, let's say, the displacement, or the concentration, or whatever the variable is with respect to time. That's equal to the velocity of the wave squared times the second derivative of the variable with respect to position. We're going to talk about wave equation. We can also talk about diffusion equation. So in the diffusion equation, we have the first derivative of the variable with respect to time. So this is the wave equation. This is the diffusion equation, or differential equation uses first order in time and second order space. So in the next video, I'm going to talk about the details of how to implement these using finite difference. So stay tuned and thanks for watching.